Hello, this is part 7 of a playlist about the preparation of alkynes. This video is about the generation, stability and synthetic uses of Arynes and strained cycloalkynes. These compounds have short half-lives only, but can react in a predictable and synthetically useful way. Arynes were first proposed as intermediates to explain strange regioselectivities of aromatic nucleophilic substitutions. Starting at the lower left corner of this scheme, when aryl halides or sulfonates are treated with strong bases, beta elimination can occur and nucleophiles can add to Arynes at two different positions. Other strategies to generate Arynes include the oxidation of aminobenzotriazoles, the fragmentation of diazonium salts, the pyrolysis of phthalic acids or anhydrides, the metallation of 1,2-dihaloarynes, and the decomposition of various functionalized aryl sulfonates. I've sketched here some of the typical reactions of Arynes. These include 2+2 cycloadditions and ene reactions with olefins, Diels-Alder reactions, 1,3-dipolar cycloadditions, and the addition of nucleophiles. Arynes are electrophilic intermediates and almost never react with other electrophiles. Their reactivity is similar to that of maleic anhydride or tetrafluoroethylene. Sometimes a reaction yields products that could originate from an intermediate aryne, but this is no proof of the formation of an aryne. The same products may have arisen by other mechanisms, and this will have to be checked case by case. The results shown here were those which originally hinted at the existence of arynes. Nucleophilic substitution of chloride from 2 or 3-chloroanisole by an amine yielded the same meta-isomer. A common intermediate seemed to be a plausible explanation of these results. Under aprotic conditions, the aryl anion formed after addition of a nucleophile to an aryne can also be trapped by other electrophiles than protons. In this example, an aryne was generated by dehydrochlorination of an aryl chloride, and reaction with a silylphosphine yielded an aryl silane. Arynes can undergo 2+2 cycloaddition to electron-rich alkenes, including enolates. Here, benzene was generated at low temperature by lithiation of 1,2-dibromobenzene with phenyllithium. The aryne then added to an amino acid enolate. Interestingly, the final product hadn't racemized completely, and the enolate thus retained some of the stereochemical information. Cycloadditions can proceed in a concerted or in a stepwise fashion. Concerted meaning that both new bonds are formed simultaneously, without any intermediate. Concerted thermal 2+2 cycloadditions are forbidden and should therefore proceed by two steps with an intermediate. As I'll show you later, this seems in fact to be the case for aryne cycloadditions, and the intermediate is similar to the aryl anions formed by addition of anionic nucleophiles to arynes. Like aryl halides or sulfonates, triaryl sulfonium salts may fragment into arynes when treated with a strong basis. In this example, the aryne underwent Diels-Alder reaction with furane. No displacement of bromide occurred. Here, the aryne was generated from an acetanilide by heating with 4-chlorobenzoyl nitride. Ene reaction with octene gave a high yield of a mixture of allyl arynes. In the absence of nucleophilic reactants, arynes can dimerize, trimerize, or otherwise oligomerize. The result generally depends on how the aryne was generated, and thermolysis in an inert solvent is about the cleanest way to generate arynes free from any nucleophiles. Heating 2-diazonium benzoate in dichloroethane gave a low yield of biphenylene. One popular way to generate arynes is by treatment of 2-haloaryl silanes with fluoride. Silicon-fluorine bond formation and halide elimination yields the aryne. Fluoride is a poor, strongly solvated nucleophile that does not normally add to arynes. In this example, the aryne formally inserted into the nitrogen acetyl bond of a trifluoroacetanilide by 2+2 cycloaddition to the enolized amide followed by ring cleavage. This is an example of palladium-catalyzed aryne trimerization. Like in the previous example, the aryne precursor was an aryl silane with a good leaving group, triflate in this case. Iodide can add to arynes and yield two metallated iodoarynes, which may be trapped by various electrophiles. Here the intermediate anion reacted with 4-nitrobenzaldehyde to the expected secondary alcohol. Not only triflates but also arene sulfonates can be suitable leaving groups for the generation of arynes, as shown here. The intermediate benzene underwent 1,3-dipolar cycloaddition with butyl acide in fair yield. Enolysable ketones can react with arynes as sketched here, by 2+2 cycloaddition to yield a benzocyclobutanol followed by ring fission. For example, when a slight excess of benzene was generated in the presence of methyl acetoacetate, the methyl ester of 2-acetyl-phenylacetic acid resulted. Substituted pyridines can also be converted into pyridines, as in this preparation. Cycloaddition to a urea followed by ring opening gave a high yield of a pyridine 3-carboxylic acid derivative. No other isomers were formed. If protons are available, benzene can be used as a soft, electrophilic phenylating reagent. In this example, a ketoester-derived enamine was phenylated this way, exclusively at carbon. Because the amine auxiliary was chiral and enantiomerically pure, the phenylation proceeded enantioselectively. No alkylation at nitrogen or at the reactive anthracene substructure occurred. Also in this example, no 2+2 cycloaddition to the enolysed amide, but just a twofold electrophilic phenylation took place. When comparing this example to the 2+2 cycloadditions to amides or ureas shown earlier, there's no obvious reason for the diverging results. However, these electrophilic arylations indicate that 2+2 cycloadditions of arynes do not proceed in a concerted but in a stepwise fashion, with a deprotonated arene as intermediate. Fast protonation of this intermediate then yields the arylated product and not a cycloaddition product. Saturated cyclohexane and larger cycloalkynes are more stable and longer lived than arynes, as shown here. While the estimated half-life of benzene in a 0.1 molar solution is estimated to be around 1 nanosecond, that of cyclohexane is more in the order of seconds. Larger cycloalkynes become even more stable, with the cyclooctane being even stable at room temperature. Nevertheless, these compounds are highly reactive and electrophilic and show some diradical character because of the bent, weakened triple bond. Here, for instance, a substituted cyclooctane was prepared by dehydrobromination of a vinyl bromide with sodium methoxide at room temperature. Nevertheless, cyclooctanes are more energetic than 8-membered cyclic allenes and will isomerize to the latter and then to 1,3-dienes with suitable catalysts. Most of the elimination strategies presented in part 1 of this playlist can also be used to prepare strained cycloalkynes. In this example, methyl cycloheptine was generated by alpha elimination of phenyl iodide from a vinyl iodonium salt, followed by rearrangement of a vinylidene. Here the alkyne underwent Diels-Alder reaction with tetracyclone and decarbonylation. Also cyclohexane has been generated by elimination, and with enolates it can undergo 2+2 cycloadditions, like arynes do. Oxidation of aminotriazoles is another strategy to generate strained alkynes. In this example, cyclohexane was generated this way, by oxidation with lead acetate at low temperature. A high yield of the Diels-Alder adduct was obtained. Heterocyclic 6-membered alkynes have also been investigated. Here a tetrahydropyridine reacted with ethyl diazoacetate to a pyrazole. In this example, a heterocyclic alkyne reacted with a biphenylyl palladium complex to a substituted phenanthine. A benzyl carbamate and an aldehyde acetal remained unchanged. Like arynes, cycloalkynes are also electrophilic and can act as soft vinylating reagents. Here a ketoester-derived enamine was vinylated at carbon in good yield with oxacyclohexane. Here are some further examples which you can also find in the description of this video. Under the Community tab of my channel you'll find a PDF version of the slides. This was the last video of this playlist, and I hope you found it useful. Thanks for watching and stay tuned for more videos about organic synthesis.